welcome back to Chemistry 3120. JP here. Today is lecture 6. Today we're going to talk about catalytic hydrogenation. Okay, so in this unit, we're going to talk about how hydrogen can be used as a reducing agent to reduce a variety of functional groups. And we're going to be talking about two main classes of hydrogenation. We're going to be talking about homogeneous hydrogenation and heterogeneous hydrogenation. So, with something like heterogeneous hydrogenation, you typically have a metal surface and you have hydrogen adsorbed onto that surface. So you have seen these types of hydrogenations before. Some good examples include things like hydrogen over palladium and carbon. And it's called heterogeneous because the palladium-carbon material surface is not miscible in the solvent that we're using. Other examples include things like hydrogen over maybe something like a platinum metal, maybe something like platinum dioxide. So these are very common examples. So these are typically right, two phases, and then homogeneous catalysis involves the metal catalyst dissolving in the organic solvent. And without getting into too much detail, we'll talk about an example today where you can have hydrogen adsorbed onto a rhodium catalyst, and then you'll have a variety of different ligands attached. And then that reduction can reduce, again, a variety of different functional groups. So what else can I tell you about hydrogenation? You need the catalyst in order to get that efficient transfer, because you need to adsorb that hydrogen onto the surface, and your molecule of interest is going to interact with that metal. So you cannot have a balloon of hydrogen, for example, and add your functional group. You really need to have that catalyst core in order to get that reaction to happen. So often for these types of reactions, the heterogeneous, the H2 is adsorbed to a surface. Typically, this is done in a pressurized system around, for hydrogenation, often 50 to 60 psi's. So that's fairly high pressure. And this is also known as a par shaker, especially for things like H2 over palladium and carbon. And so let's go and talk about a functional reaction that involves hydrogenation. All right, so let's look at the stereochemistry, or what happens when we take a double bonded 6-membered ring, and ask, how does that get hydrogenated? What's the mechanism? How does it get adsorbed onto the surface? So let's take a look at this molecule here. So let's call this mechanism for heterogeneous hydrogenation of double bonds. And specifically, we're going to look at this molecule here. this six-membered ring with two methyl groups and a single double bond. And if we hydrogenate this, let's call this H2 over, let's just call this a metal catalyst. You know that you're going to reduce this double bond and you're going to generate this structure here with your new hydrogens attached. But let's think about the stereochemistry and how these interactions actually happen. Okay, so let's draw our metal surface. And here's, you can imagine a metal surface and there's lots of hydrogen atoms that are adsorbed onto that metal surface. And typically the metal is slightly electropositive, so it's attracted to electrons, things like double bonds, triple bonds. So if we take our molecule here and let's imagine this is going to float and come close to the metal, there's going to be some type of weak interaction as it gets closer and closer to that metal surface. And what's going to happen is we typically don't draw mechanism arrows for these types of transformations, but I think it's useful to see how these bonds are made during that interaction. So I will draw them in this blue color here, just sort of lightly, just so you can see how the bonds are made. So you can imagine if this thing comes closer, you're now going to be able to transfer a negative hydride to this double bond here. And if you do that, you're going to break this pi bond and it's going to form a carbon metal covalent bond complex. So if we do that, you can see here we have a six-membered ring. We're losing our sp2 center, so we're going to have a six-membered ring with all sp3 centers. So the best way to draw a six-membered ring that has sp3 carbons throughout is to use a chair structure. So let's draw this now as a chair structure. Okay, so we have our metal carbon bond here. Here is our newly added hydrogen. Here is our methyl group. And then what we have over here is we have our methyl group pointing this way in order to make this carbon metal interaction. And then also keep in mind that you have lots of hydrogen atoms around. So what's going to happen is you're going to now get transfer of this hydrogen here, and the bond here will come down, and you'll break off that carbon bond. So if you do that, you're going to generate this structure here, where you have your methyl group on this carbon. This is in the axial position. And then you have this methyl group here in the equatorial position. And here are your hydrogens. Again, now this hydrogen is in the axial position. This one is in the equatorial position. So in order to demonstrate the stereochemistry of this product in a six-membered ring format, I'm just drawing this equal sign. 3 dashes corresponds that this is equal to this structure here where you have your two methyl groups on the same side. Okay, so this corresponds to a cis product. Or sometimes we will call this a syn product, meaning that they are on the same side. Okay, so if the hydrogens are delivered from the same face, are both delivered this is the product that we get. Now, is that the only product that we're going to get during this reaction? So I'm going to give you an example in which we do this reaction with a metal catalyst, and we will typically do this with some acetic acid in it. All right, so let's draw out, and this is our solvent, just to help solvate the materials. And let's draw acetic acid. So if we have acetic acid in solution, we're going to have a lot of protons, but we're going to have a lot of conjugate base present. And one of the things I want to point out is that this carbon-metal bond here, it's not, it's hard to depict this as a real covalent bond. It's a loosely connected bond in which it's relatively easy to break this carbon-metal bond. So any opportunity to break this, whether it's a nearby hydride that comes in or some other method to release that from the metal, the molecule will perhaps take that choice. So under these conditions, I'm going to draw a couple protons up here, right? These are here, they're implied. And we're going to have a lot of conjugate the conjugate base of acetic acid present. And if this hydrogen takes too long or it's not around, the other thing that can happen is that you can actually get removal of this proton via elimination to form a double bond, a new sp2 center, and then you can break this carbon-metal bond. If you do that, you are now going to have a molecule that will look like this. A chair conformation. Okay, I'm drawing it as a chair, even though it's not really a true chair. There is a double bond here, but you'll see why in a minute. Here we have our methyl group. Keeping consistent with the geometry of this sp2 center, we now put our methyl group over here. Okay, so this molecule now is free to leave, but it comes back because you have metal surfaces present, right? It's a catalyst. So I'm going to draw your metal surface, and attached to that, we're going to have hydrogens present as well. So this is going to form some type of interaction like we'd seen earlier because you have that double bond. And what you're going to see happen is that you're going to get that transfer of the hydride to that carbon and then form this carbon metal complex. So if that happens, you're now going to generate here's your metal, here's your methyl group here. Here you have hydrogen that added in the equatorial position, methyl in the axial position. And then finally, when you add another hydrogen atom, so I'm just going to go here and continue drawing the structure right over here. Before I do that, I'm just going to clean up this chair structure just a little bit. Not 100% happy with it. These lines should really be parallel. There we go. These two lines here. That's a better looking chair structure. And when that happens, I need to get my markers. Don't go away. You'd think I'd be prepared and have everything at the board with me, but yeah, even after lecture 7, forgot this. So anyways, I got my markers, and if you do another hydrogen atom addition, right? You have lots of hydrogen atoms, adds to this, breaks that bond. What you're going to end up generating is this compound here with a methyl group. That was fixed from the beginning. You have this carbon here like that. And of course you have hydrogens on all the other carbons. So this compound here looks very different from that one there in terms of its stereochemistry. So in fact, this here corresponds to, you have two methyl groups that are both axial. So this corresponds to methyl groups that are actually going to be trans to each other, or sometimes we call this anti. Okay, so when you do this reduction, you could get potentially two different products, the syn product or the trans product. How do we know what the major product is going to be? So I'll just share with you some data from two reactions looking at heterogeneous hydrogenation. So if we use the same substrate and we do this reaction with H2 over palladium and carbon with acetic acid, it turns out that we generate two cis products, the cis and the trans. The cis product that's shown here is going to be the same as the one here. This one is formed in about 16% yield, whereas the trans is formed in about 64% yield. Okay. If we do the same reaction with hydrogen, of course, but with a different metal catalyst, this time platinum dioxide, keeping acetic acid as our solvent, the numbers completely change. We get around 82% cis and 18% trans. Okay, so depending on the type of metal that you use will dictate and will govern the cis to trans ratio of those products. Now let's talk about why that is. So why do we get different ratios between both of these? Now let's talk about the second reaction first. So with platinum dioxide, we generate not exclusively, but 82% as the major product of cis, which is this mechanistic pathway up here. So the hydrogen are both delivered from the same face to give us a cis product. That must mean that the likelihood of this breaking through this elimination reaction probably doesn't happen very frequently. So therefore, what this means is that the ability of the molecule to come on and off the catalyst determines that cis to trans ratio. So if it comes on and it's fixed, then it's going to wait for this hydrogen to come on, and then we're going to generate this product here. So, however, for this platinum-carbon reaction, you can see that it must follow pathway 2, because in order to generate more of the trans product, the compound must have come off the catalyst. Perhaps twice, like I've shown here, or maybe even a third time. So the ability of the molecule to come on and off the catalyst determines the syn or the cis to trans ratio. The ability of the molecule to come on and off determines the cis to trans ratio. Okay, so for this reaction here, the molecule can come on and off the catalyst much easier compared to this one here, because we get a higher trans ratio for this top reaction, higher cis ratio for the bottom one. You can see too, one last note here, that these two numbers here add up to 100%. So these are isolated yields. These two numbers here don't add up to 100%. This is likely due to some other impurities in the reaction. This one here is a bit more of a dirtier reaction, so you don't get complete conversion. Whereas this one here looks much cleaner, and your isolated yields actually match up to 100% total. Okay, so that's the mechanism of hydrogenation. I want to show you a catalyst that you've seen before in second year organic. And this catalyst here is good at reducing triple bonds. So we're going to take the hydrogen, we're going to use palladium, but we're going to use a calcium carbonate mixture, and then we're going to add something called quinoline. Quinoline looks like this. Okay, if we do this reaction, we take this triple bond, a number of different things could happen. So you can imagine the triple bond will come coordinate to the metal complex, and then hydrogen will add to it. And the first time it happens, we're going to go from a triple bond to a double bond. Now, if you do this reaction with these conditions and add this molecule here, you're going to end up generating this compound here, which is a double bond, and this is a cis double bond. A cis alkene. And where have you seen this type of reaction before? It's a controlled hydrogenation, and it's also known as the poisoned catalyst. Okay, so this is poison catalyst, and what's happening is that you can imagine you have your metal surface. You can make a reaction happen making the cis alkene. What this tells you is that the hydrogens must add on the same face pretty much at the same time. But once this is made, why doesn't this go on to the metal catalyst like we've shown there and reduce this fully to an alkane? So the reason we don't get further hydrogenation is because this is also known as a poison catalyst, where we have quinoline, which now has a double bond, lots of double bonds, and that's really going to poison the catalyst, so other double bonds cannot react. So this catalyst here is called Lindlar's catalyst. And very likely in second year you learned about Lindlar's catalyst, but we're just given these conditions, or learn that it was a poison catalyst. But now I think you can imagine more specifically how this will work. So just writing down what I said, this poisons the catalyst so that hydrogenation of the double bond does not occur. Okay, so these are all examples of heterogeneous catalysis. And what I'd like to do is just spend a few minutes talking about homogeneous catalysis. All right, so where is my eraser? Here it is. Heterogeneous catalysis. So homogeneous, heterogeneous. Homogeneous is going to involve rhodium. And one metal that we're going to look at extensively is rhodium, with a number of different ligands attached to it. So homogeneous catalysis have different reactivity compared to heterogeneous catalysis. And quite often you can get reactivity towards different functional groups compared to heterogeneous catalysis. And you can react things with greater specificity. And the best thing to do is to show you some examples. So here is an example of a molecule that has a couple different double bonds. And if we treat this with hydrogen over a rhodium catalyst, so this is going to be, we're going to have triphenylphosphine. And we'll talk about that in a minute. So there's 3 of these with a rhodium center and then a chlorine attached to it. We typically do these in organic solvents. What this will do is this will select actually this less sterically hindered double bond, reduce that, but not touch this one here, which is more stable and more branched. So that's an example of controlling chemoselectivity using a homogeneous catalyst. Another example that I'll talk about, or that I'll put out here, is this, where you have an ester and of course aromatic rings, and you have this double bond here. Using a homogeneous catalysis identical to the one shown, you can actually selectively reduce just this double bond, not touch the aromatic rings, not touch the ester. So very, very powerful in its chemo selective nature. And again, I'm just showing you benzene because that's the organic solvent. So let's talk about the mechanism of how homogeneous catalysis work. Okay, so let's take a look at this rhodium center. And this rhodium has 4 different things attached. It has this triphenylphosphine, so it's this phosphorus with 3 phenyl groups, so that's fairly large. And then what happens is that the hydrogen comes in, and this needs to adsorb and actually make covalent bonds with the rhodium catalyst. Now, rhodium can only handle so many bonds, so in order for hydrogen to come in, it's going to have to remove a few things. Okay, so what's going to happen is that one of these ligands here, the triphenylphosphine, is going to leave, and you are now going to have a complex with 5 ligands. Two are triphenylphosphine, 2 are hydrogens, 1's chlorine. So this comes in, and I'm just showing you that comes in and kicks off a triphenylphosphine. Okay, so this rhodium, so during this process, rhodium is in the +1 oxidation state, and here it's in the +3 oxidation state. So at this stage here, the rhodium is now much more willing to react or to form ionic bonds with double bonds. So let's take a look at very simple double bond here, and you're going to have some type of interaction with that rhodium center, very similar to the mechanism with double bonds onto the metal surface. So again, we typically don't draw reaction arrows with these types of transformations, but I think when you're learning them, it's helpful to see how electrons might move in order to form these bonds. So one of the first things that happens is that you can imagine this hydride attacking this carbon here, and then similarly to what we'd seen before, you form this carbon-rhodium complex. Okay, so we get that interaction, that bond interaction happening. And if we do that, we will have there's our newly added hydrogen there. I'll just put these methyl groups because I drew them in over there just to make sure that it's complete. And then essentially what happens next is we're going to get this hydride reacting here and then releasing that off. And then you can see we now have a new product that will not have a double bond, but will be now an alkane. Now this is where the triphenylphosphine comes into play, the one that got released off. And essentially what it's going to do is it's going to say, hey, wait a minute, I didn't like getting pushed off in the first place. There are free electrons on that phosphorus. It's going to come in and initially react at that rhodium, and then you're going to get this transfer to that carbon here, and then you're going to break that carbon-rhodium bond. Again, I'm just drawing them in dotted lines because we typically don't draw arrows for these types of reactions, but it helps to see how those bonds are connected. And so at the end of the day, you go back to that same rhodium catalyst. And your product is now going to be this reduced compound, which is now an alkane. And you can imagine if you had some stereocenters here, then you could generate a cis compound. And it typically happens, like I'm showing you, only once. So this is very good at selectively reducing double bonds in this cis type of fashion. Homogeneous catalysis are ubiquitous in organic chemistry. I'm just showing you one example with this rhodium metal. If you decorate, for example, the rhodium metal with different ligands, that will change its ability to interact with different functional groups. These are fairly large. You have a phosphorus with 3 phenyl groups. So you're really going to be looking for the easiest double bond to get. So in these cases here, this one is the low-hanging fruit. This one's too sterically hindered to get access to. This is like a benzylic double bond that's quite reactive compared to some of the other functionality, so that's why that reacts first. By changing some of these substituents on the rhodium metal, you can definitely change its functional group preference for these types of reactions. So again, you generate this rhodium 1, and then hydrogen will come back again, and you can see that it's a catalytic cycle. Okay, one other thing. This is called Wilkinson's catalyst. So it does have a name. Okay, I hope you enjoyed lecture 6 on catalytic hydrogenation. See you soon for lecture 7.